Welcome back to our channel. In today's video, we'll talk about some celestial objects that fascinate almost everyone, thanks to their colors and shapes. I'm talking about the spectacular nebulas. Let's start by saying that there are mainly three types of nebulas: emission nebulas, reflection nebulas, and dark nebulas. In today's video, I want to give you an overview of the first type of nebulas, the emission nebulas. In the next two videos, we'll look at the other two types together. With these videos, we will understand the physical mechanisms behind their beautiful colors. Before we start, as always, I invite you to subscribe to the channel and activate the bell to always be notified whenever a new video comes out. First of all, what are nebulas? Nebulas are clouds composed of gas and dust present in the interstellar medium. The interstellar medium refers to the material found between stars within a galaxy. The gas in this composition, and thus of the nebulas, is primarily composed of hydrogen, which represents about 70% of the mass of the interstellar medium, and helium, which constitutes about 28%. The remaining 2% of the mass of the interstellar medium is composed of heavier elements, which can be found in both gaseous form and as dust. Hydrogen is the most widespread element in the entire universe and is also a very simple element. In fact, a hydrogen atom consists of a single proton and a single electron orbiting around it. Interstellar dust is very different from the dust we are used to. It is composed of small solid particles mainly made of carbon-based molecules and metals such as iron or magnesium. We will talk about interstellar dust in more detail in the next two videos. Emission nebulas, as the name suggests, are nebulas whose light is emitted directly by the atoms that compose them. Depending on which atoms make up a nebula, we will have different colors. There are mainly three types of emission nebulas: H regions, planetary nebulas, and supernova remnants. The physical mechanism underlying the emissions is similar for all three types of nebulas. Let's first talk about H regions. These are classified as diffuse nebulas, meaning clouds of gas that are extended without a well-defined boundary. H regions are nebulas composed mainly of ionized hydrogen. In fact, the H stands for ionized hydrogen. H regions surround newly born massive stars. These types of stars are very hot, blue in color, and very bright, emitting a lot of UV radiation, ultraviolet rays. It is precisely this radiation that ionizes the hydrogen atoms in the interstellar medium surrounding them. The ultraviolet rays emitted by these stars are so energetic that they strip electrons from the hydrogen atoms of the interstellar gas near these stars. At this point, the hydrogen is said to be ionized. When these electrons recombine with the nucleus, meaning they start orbiting the nucleus again, they emit light, typically red, which gives color to these nebulas. Almost all red nebulas are H regions. These nebulas can extend up to a few hundred light-years and, after a few million years, tend to be swept away by the strong stellar winds of the young stars within them. An example of an H region is the Rosette Nebula. This H region has a diameter of about 130 light-years and a total mass of about 10,000 times the mass of the Sun. Inside it are young, hot, newly born stars. The second type of nebula I want to talk about is the planetary nebulas. This type of nebula has nothing to do with planets. Their name only comes from the fact that their typically circular shape reminded early astronomers of the shape of a planet. These nebulas are composed of material expelled by low-mass stars towards the end of their life. Specifically, what happens is that low-mass stars, up to about 8 times the mass of the Sun, tend to expand towards the end of their life, becoming cooler and redder, meaning they become red giant stars. In the final stages of their life, these red giant stars begin to pulsate, dispersing their outer layers into the surrounding space. At that point, their hot and very compact core, known as a white dwarf, is exposed. All the expelled material forms the planetary nebula. It is thought that the Sun will also become a white dwarf at the end of its life, leaving behind a planetary nebula. These nebulas, unlike H regions, are not composed only of hydrogen but also of other elements such as oxygen and nitrogen. When these atoms are hit by the energetic radiation from the white dwarf at the center of the nebula, they become ionized. Again, when the electrons recombine with the nucleus, they emit energy in the form of light. The electrons of these atoms may also not be completely stripped away but can simply absorb the radiation, becoming more energetic. In this case, they are said to be excited. When the electrons return to their initial state, or de-excite, they release energy in the form of light. The light emitted when the electrons recombine or de-excite gives color to planetary nebulas. However, this time, the color of the emitted light depends on the particular atoms that make up the nebula. This is why planetary nebulas have very varied colors. An example of a planetary nebula is the Ring Nebula. It is a beautiful nebula with a diameter of about 1 light-year and can be observed in the constellation Lyra. At the center of this nebula is the hot white dwarf that ionizes the gas of the nebula. It is this gas that is responsible for the beautiful colors of this nebula. Specifically, the blue color is due to the presence of helium, the green color is due to oxygen, and the reddish color seen in the outer regions of the nebula is due to the presence of sulfur and nitrogen. Another example is the famous Dumbbell Nebula. This nebula, located about 1,200 light-years away in the constellation Vulpecula, has a typical double cone shape, resembling an hourglass. It is also composed of the outer layers lost in the final stages of a low-mass star's life. Its double cone shape indicates how the expulsion of the outer layers of stars in the final stages of their life may not be uniform in all directions, but rather the material can be expelled in 2 specific directions, forming 2 cones. A fascinating hypothesis is that most planetary nebulas actually have a double cone structure. This would also apply to circular planetary nebulas. In that case, the 2 cones would be aligned towards us, making it look like an hourglass viewed from above. These strange shapes are the result of the complex mechanisms of material expulsion that occur in the final stage of a star's life. Mechanisms that can lead to very peculiar and intricate structures, as in the case of the Cat's Eye Nebula, or can lead to symmetrical and mysterious structures like in the case of the Owl Nebula. Finally, let's talk about the third type of emission nebula, the supernova remnants. When stars with a mass greater than about 10-12 times the mass of the Sun run out of the fuel necessary for nuclear reactions towards the end of their life, the pressure that keeps their outer layers balanced is lost. Consequently, these layers begin to collapse under their own weight. This collapse is followed by a rebound that generates a gigantic explosion called a supernova explosion, dispersing all the stellar matter into space. This material, ejected at supersonic speeds, is heated to extremely high temperatures by the immense energy released during the explosion. Nebulas that originate from supernova explosions are composed of the remains of the exploded star, meaning the material expelled during the explosion. This is why they are called supernova remnants. The gas that makes up these nebulas is composed of ionized atoms due to the extremely high temperature. Again, the magnificent colors of these nebulas are due to the electrons recombining with different types of atoms, emitting light. The different colors indicate the electromagnetic radiation emitted during a supernova explosion, which ranges from radio waves to X-rays and gamma rays. The sources of these radiations are related to other physical processes that we might cover in detail in other videos. An example of this type of nebula is the famous Crab Nebula. It is about 6 light-years in size and was formed from the remains of a supernova. Its colors indicate the different types of atoms present. For example, green is due to the emission from recombining ionized sulfur, while the red regions are rich in oxygen. The bluish light seen in the central regions is generated by free electrons moving at near light speeds in the magnetic field present in those regions. Sometimes, images of nebulas, just like the Crab Nebula, are in false colors. These colors do not reflect the true colors of the nebula. This image processing is mainly done for 3 reasons. The first is to highlight details, the second is to better understand the chemical composition of the nebula, and the third is because sometimes, to compose the image of a nebula, other images captured at wavelengths that the human eye cannot perceive, such as infrared or X-rays, are used. In the case of the Crab Nebula, what I said before still applies. The light we receive from the different regions of the nebula is due to the emission of light by electrons recombining with different types of atoms. The red light is partly due to the presence of hydrogen, while in the outer layers, pale green light emitted by oxygen can be observed. I would like to conclude this video by talking about the spectacular cosmic reef. The cosmic reef is composed of 2 emission nebulas present in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. The cosmic reef owes its name to its resemblance to an underwater scene. The larger, coral-shaped red nebula is NGC 2014 and is a star-forming region. It is precisely the strong winds from the young blue stars present in the nebula that shape it, giving it the shape of a coral. This nebula is an H region. In fact, its red color is due to ionized hydrogen atoms recombining. The blue nebula is called NGC 2020 and is composed of matter expelled by the star at the center of the nebula. Its color is due to the electrons of the oxygen atoms in the nebula, which, after being excited, emit visible blue light. From the beauty of this scene, it is not difficult to understand why it was chosen to celebrate the launch of the Hubble Space Telescope, the instrument that captured this image. I hope this video has given you a comprehensive overview of the physics behind emission nebulas. In the next video, we will look at reflection nebulas together. So, make sure to subscribe to the channel to not miss anything and leave a nice like.